Welcome to this lecture on Bend's rule. Have you ever wondered why molecules are rarely perfectly symmetrical, even when our basic model suggests they should be? Today, we are going to explore a fascinating principle that explains how atoms dynamically adjust their shapes to accommodate different neighbors. By the end of this video, you will understand exactly how to predict these subtle molecular distortions. Before we dive into the chemistry, let us picture a simple analogy. Imagine a parent holding hands with two different children while walking down the street. One child is very independent and constantly pulls away, so the parent extends one arm fully outward. The other child is timid and prefers to stay tucked in close, so the parent keeps that arm bent and near their body. In chemistry, a central atom acts exactly like this parent. It dynamically adjusts its arms, which are its electron orbitals, depending on how strongly the attached atoms pull on the shared electrons. This intuitive adjustment is the core of Bend's rule. Now that we have our analogy, let us define two key chemical terms. First is electronegativity, which is simply an atom's ability to attract shared electrons toward itself. Highly electronegative atoms are greedy for electrons. Second is S character. When an atom forms bonds, it mixes spherical s orbitals and dumbbell-shaped p orbitals to create hybrid orbitals. The s character is the percentage of the original s orbital in that mix. Because s orbitals are spherical and close to the nucleus, an orbital with high s character holds electrons very tightly. Conversely, orbitals with high p character are longer and place electrons further away. With those terms clear, we can now state Bend's rule formally. The rule states that atomic S character concentrates in orbitals directed toward electropositive substituents. In simpler terms, if a central atom is bonded to a greedy, highly electronegative atom, it gives up trying to hold those shared electrons close. Instead, it directs a longer, p-rich orbital toward that greedy atom. It then saves its tightly held s-rich orbitals for atoms that are willing to share nicely, or for its own unshared lone pairs. By doing this, the central atom stabilizes the entire molecule. This conceptual rule actually has a mathematical foundation, which brings us to Coulson's theorem. This formula directly links the fractional s character of a hybrid orbital to the cosine of the bond angle between two identical bonds. In this equation, theta represents the bond angle measured in degrees and capital S represents the fractional s character expressed as a decimal, for example 0.25 for an sp3 orbital. Because the cosine function is negative for angles between 90 and 180 degrees and s is a fraction less than 1, the math perfectly balances out. As s character increases, the fraction becomes more negative, meaning a wider bond angle. Now that we have our formula and concepts, let us see this in action with a concrete example. We want to determine the exact three-dimensional structure of the molecule phosphorus dichloride trifluoride. We start by looking at the central phosphorus atom, which is bonded to 5 other atoms with no lone pairs. Having 5 electron domains means it must use sp3 dehybridization. The standard geometry for this hybridization is a trigonal bipyramid, which looks like two triangular pyramids glued together at their bases. Our goal is to figure out exactly where the fluorine and chlorine atoms go. Continuing with our strategy, we need to evaluate the positions available. First, we compare the electronegativity of the attached atoms. Fluorine is the most electronegative element, meaning it pulls electrons much more strongly than chlorine. According to Bend's rule, fluorine will demand hybrid orbitals with the least amount of s character. Next, we look at the trigonal bipyramid's positions. The two axial positions, pointing up and down, are formed by p-d hybrid orbitals, which have exactly 0% s character. The three equatorial positions around the middle are formed by sp2 hybrid orbitals, giving them roughly 33% s character. This brings us to the final placement of the atoms. Because fluorine is more electronegative, it prefers the position with the lowest possible S character. Therefore, the fluorine atoms will naturally occupy the axial positions, which have 0% S character. Since there are 3 fluorine atoms but only 2 axial positions, 2 fluorines will take the top and bottom spots. This forces the third fluorine to take one of the equatorial spots. The 2 less electronegative chlorine atoms will happily occupy the remaining 2 equatorial positions, which have higher S character. This arrangement perfectly minimizes the energy of the molecule. Let us visualize the result we just derived. On screen, you can see the trigonal bipyramidal structure of our molecule. Notice the central phosphorus atom. The vertical axis holds 2 fluorine atoms in the axial positions, which are formed by the PD hybrids with 0% S character. The angle between the axial and equatorial plane is 90 degrees. In the horizontal equatorial plane, we see the remaining fluorine and the 2 chlorine atoms separated by 120-degree angles. This diagram perfectly illustrates how Bend's rule dictates the physical arrangement of atoms based on their electronegativity. Now that we have seen how atoms choose positions, let us look at another example to predict bond angle deviations. We will analyze difluoromethane. The central carbon atom is bonded to 2 hydrogens and 2 fluorines with no lone pairs. This means it is sp3 hybridized and its basic shape is tetrahedral. In a perfect tetrahedron like methane, all bond angles are exactly 109.5 degrees. Our strategy is to determine how the differing electronegativities of hydrogen and fluorine cause the carbon atom to reallocate its S character among its 4 bonds. Continuing with our analysis, we start by comparing the electronegativities of the attached atoms. Fluorine is highly electronegative, while hydrogen is relatively electropositive compared to carbon. According to Bend's rule, the central carbon atom will not distribute its S character equally. Instead, it will direct less S character, meaning more P character, toward the greedy fluorine atoms. Consequently, it will direct the leftover, higher S character toward the hydrogen atoms. This unequal distribution is the key to understanding how the bond angles will shift from their ideal values. This unequal distribution leads us directly to our final answer. Because the carbon-fluorine bonds receive less S character than the ideal 25%, the angle between them must decrease. As we learned from Coulson's theorem, a decrease in S character results in a narrower bond angle. Therefore, the angle between the 2 fluorine atoms is squeezed to less than 109.5 degrees. Conversely, the carbon-hydrogen bonds receive more S character, which results in a wider bond angle. The angle between the 2 hydrogen atoms will open up and be greater than the ideal tetrahedral angle. Before we conclude, let us understand why predicting these subtle distortions matters in the real world. In fields like pharmaceutical drug design, molecules are rarely perfectly symmetrical. The exact 3-dimensional shape of a molecule determines whether it will fit into a specific protein receptor in the human body, much like a key fitting into a lock. If a chemist substitutes a hydrogen atom with a fluorine atom, Bend's rule dictates that the entire geometry will subtly shift. Bond angles will change and bond lengths will alter because bonds with more S character are shorter and stronger. Understanding this is crucial for designing effective drugs. We have covered a lot of ground today, so let us review our key takeaways. First, Bend's rule provides a logical bridge between an atom's electronegativity and the physical shape of the hybrid orbitals it uses to bond. Second, remember that highly electronegative atoms draw longer p-rich orbitals toward themselves, forcing the central atom to use its tightly held s-rich orbitals for electropositive atoms or lone pairs. Finally, by mastering this rule, you can easily predict which positions atoms will take in complex geometries and exactly how bond angles will deviate from their ideal textbook values. Great job following along.